Hi, my name is Brandon Graisley. I'm a high school math teacher. We are transforming sinusoidal functions, and this is part 2, where we're looking at a change in period. And if you haven't already watched part 1, you're going to need to know that for the end of this video, so you might want to go back and start there if you haven't been there already. So let's look at graphing the function sine of theta, and a transformed version of this function, sine of 2 theta. And you'll notice that I've put that in brackets to be extra clear. Here we have sine of theta, no brackets. You don't strictly need these here, but it's a good practice to put brackets around to contain that number. So, how do we graph both of these? Let's start by just graphing the sine of theta. So I'm going to put 90 degrees here, 180. I'm using every 4 squares as my scale. And then I'll get to 360 right here. And vertically, I don't know, I like it about there. 4 boxes to give me 1 and down 4 for -1. Theta axis and y-axis. Let's start by graphing sine of theta. It starts at 0, 0. As a peak at 1, 90 degrees and 1. Back down to 0 at 180. 270 is below the axis. And 360 is on the axis again. Okay, that looks pretty nice. Now let's graph sine of 2 times theta. I'm going to grab a calculator for this because I think this part is not very intuitive. Let's see if you can see that. It's getting a little late in the day here. So sine of 2 theta, let me type sine of 2 times 90 to begin with. And that gives us 0. So when theta is 90, we're going through this spot right here. Now that might seem a little strange. Let me back up and try sine of 2 times 0. Well, that's still just 0. So we have to go through these 2 points right there. I kind of wonder what's going on in here then. So let's try sine of 2 times 45 degrees. When theta is 45, what is g of theta? That is 1. So right here, when we're at 45 degrees, the function is up here at a maximum. And maybe you can see what's happening here. I'm going to continue. I'm actually going to graph this point here, which is going to be at 135 degrees as well, to try to get more of a clue about what's happening. Sine of 2 times 135 degrees is -1. And you might realize here, if I do sine of 2 times 180, I get 0. So the function does this. It's the same range as the other function. It goes between +1 and -1. But everything seems to happen a little faster. And if I were to continue here, what you'll see happen is this. You can try this with your own calculator. You'll see exactly the same shape, but it happens twice as fast. That is, you don't have to go all the way to 360 to get through one cycle. With the original function, it took us a full cycle. It took us 360 to get through a full cycle. This one only took us 180, and we got a second cycle in. We got 2 cycles in the usual 360 degrees. All right, let's go see what happens with this graph. We have sine of theta, and then h of theta is sine of 1/2 times theta. The angle itself is multiplied by 1/2 before you do the sine. So let's see, I've got 4, 8, 12, 16. I've got 20 little boxes here. And I already know I'm going to have a bit of a problem, but we're going to go for it just like normal here. There's my 360. +1, -1. I'll graph my original sine function. that was not my best, but still okay. Now, sine of 1/2 times theta. I'm not going to use the calculator this time. I'm going to just think about it. 1/2 of theta. I'm going to start with 360 to begin with. 1/2 of 360, when theta is 360, 1/2 of 360 is 180. What's the sine of 180? It's 0. So at 360 we are going through that spot. Let's try 180 as another example. When theta is 180, I'm looking for what's the y value that I'm going to graph here. So here's my sort of x value, theta. 1/2 of 180 is 90 degrees. So maybe I will grab the calculator just to show you. Sine of 1/2 times 180 degrees is essentially like saying what's the sine of 90, which is 1. So at 180 degrees, it's in the same location as the sine of 90, half of 180. We're going to get this effect. And this curve will continue down in this direction. In fact, we didn't even get an entire cycle in. We only got half of a cycle. With this function, we got 2 cycles between 0 and 360. With this one, we only got half of a cycle in between 0 and 360. So this number that we're multiplying the angle by has an effect of changing the period. If the number is small like this, it makes the period longer. And if the number is large, like 2, it makes the period shorter. I like to personally think about it as how fast does it happen? It happens faster, more cycles in the same amount of horizontal distance because it's being multiplied by 2. Another way to think about it is this number tells you how many cycles you can get in the usual 360. 2 full cycles. Only half of a cycle in this example. So this lets us find the period. Let's try one more. In this example, we have f of theta is still sine of theta, but j of theta is sine of negative theta. That is, we're going to take the negative version of the angle before we plug it into the sine function. Now this is a very tiny looking graph, and I've done that on purpose. So let's see what happens here. 90, 180, 270, and 360. And I'm going to go to the trouble of graphing what happens to the left of the y-axis as well. Vertically, there's 1 and negative 1. Okay, original graph. And there's why I'm using a pencil, because I definitely missed that time. Okay, and then this has to continue backwards, if you like, in the other direction. So this is still our original sine function. It's periodic and it repeats in both directions forever. Like that. Okay. Now let's graph sine of negative theta. We're going to take every theta value, every x value or theta value, and we'll make it negative before we put it into the sine function. So for example, when theta is 90, we have to figure out the right y value. Sine of negative 90 will be the correct y value here. So I can grab a calculator if I want. Sine of negative 90. That's negative 1. Or I can also look over here at the graph to see where was the sine function when theta was negative 90. So I'm going to get a point down here. All of the zeros are still the same because they all match up. Zeros there, zeros there. But some of the other points are different. What do we get for negative 270? That's positive 1. Now this probably looks to you like a vertical reflection, and it kind of is. I mean, it has the same shape, or it's in the same spot as that, but the truth is it's not. It's really a horizontal reflection. We'll get the same effect in the other direction as well. So our instinct tells us that this is a vertical flip because this point looks like this point looks like this point, and so on. But if you think about it in the other direction, this point here came from, if you like, this point here. It's a reflection horizontally. Now, similar to the amplitude change, we have a period change here. So in general, multiplying the angle, notice we're not multiplying with the function, but just the angle, multiplying the angle by some number, I'm going to call it k, which is not 0. This has the effect of dividing, so multiplying by k divides the period. Take that period of 360 and cut it down by how much? By the absolute value of k. So once again, that's the positive version. Let me just write that down. If k were negative, we would use the positive version instead. So multiplying the angle by k divides the period by k. We'll go back and look at this again in a moment. And just like with the amplitude change, and it causes a horizontal reflection if k is less than 0. That is, k is negative. Now, since sine of theta and cosine of theta, they each have a period of 360 degrees, we know then that sine of k times theta and cosine of k times theta have a period of, so we take the period and divide by the absolute value of k. 360 degrees divided by the absolute value of k. So for example, in our first example, k was 2, and we had a period of 360 divided by 2, which was 180 degrees. So I have some practice questions for you to try. So the first one is to graph cosine of 2 theta along with cosine theta on this axis here. I'm going to go down to the second one though, sine of negative 2/3 theta. So the period is 360 degrees divided by the absolute value of k. Now k is negative 2/3, so I'm going to divide by 2/3. Now dividing by a fraction is not very comfortable for a lot of people. Many people will do this instead, multiply by the reciprocal of that fraction, multiplied by 3/2. So that is how long it takes to complete one cycle of this new function. Another way to think about this is that only 2/3 of a cycle will get completed over the course of 360 degrees. And I'll let you graph that as well. And then these four, to find the period of each sinusoidal function without graphing it, just by reading the equation that you see here. Be especially careful on this last one. I'm being tricky on purpose. So what happens when we want to combine amplitude and period changes? Well, that will be something like this, and we are going to graph this one together. Here we have f of theta is sine of theta, and g of theta is 3 times sine of negative 1/2 theta. So this is our horizontal change in here because we're changing the angle before we evaluate the function. The vertical change happens outside of the function. Horizontal changes in the brackets, vertical changes are on the outside. So let's begin by figuring out the amplitude and the period of this function. Remember, the amplitude of f is 1 and the period is 360. The amplitude here is just 3, that number a out front. The period we need to calculate, though we can't read it directly. The period is 360 degrees and we divide by the absolute value of this number, which would be dividing by 1/2, which will work out to 720 degrees. Another way to think of it, only half of a cycle is completed in 360, so it'll take 720 to complete the entire cycle. So I have to get up to +3, down to -3, and I have to go all the way to 720 to get to a full cycle of this function. So let me shrink my horizontal axis a little bit. Here's my 4 tick marks to get to 360. And there's 720. Vertically, I need to get to 3 on my larger function. I've got 6 boxes to work with, so let's call that 3. That'll make this 1. All right. Here's my original function. I've done this a lot of times. Hopefully it's getting faster for you. Okay, that looks lovely. Now we have 2 transformations to apply. We have to change the amplitude and also change the period and reflect the thing horizontally. So I guess we have 3 things to do. You can do these in any order you like. It doesn't actually matter. The one that can be very confusing is the horizontal reflection. So I'm going to apply the 3, the amplitude change, and the 1/2 part, but then I'm going to do the reflection at the very end. So first I'm going to graph 3 sine half theta, then I'll do 3 sine -1/2 theta. So to begin with, the amplitude change, the period change of to 720 degrees means I will complete a full cycle, one full cycle, out to 720. So it starts here, it ends here, the halfway point is at 360, and in between, so at these points here, 180, and whatever that one is, 540 I guess, we have to be at our peak and our trough, which is our 3 and -3. And then I'll do the opposite on this side. So 360 is where the 0 happens. Trough, peak, and back to 0. So I'm going to connect those. Now, once again, this is not our final function, but it's really close. Okay, so this is y equals 3 times the sine of 1/2 theta. Again, I'm missing that the negative sign there. So this is not exactly our function. In fact, our actual function is a reflection of this horizontally or across the y-axis. So I have to flip this thing horizontally. That is, every point here gets flipped to its negative angle version and vice versa. So the whole thing flips horizontally. So this point, for example, will become this point over here. The whole thing gets flipped around horizontally. Let's just draw it. Now this can get very cluttered and confusing. I would suggest that you try out a program like Desmos, play with it, desmos.com, play with changing the numbers and seeing how the function changes. You want to get good at understanding how this works, not just memorizing a list of procedures about how to flip stuff. Get good at understanding how and why. And I would really suggest that you try plugging some numbers into your calculator. See what happens when you do 1/2 times an angle and how that relates to the rest of the graph. Alright, so our final version here, the one that goes down at the beginning, that is our final function. So very difficult, let's be honest, there's a lot happening here all at once, and so we tend to show our changes gradually. Once again, I did the period and amplitude change first, and then I applied the reflection at the end because I personally find that easier. Here's some practice. Now this is getting quite tricky. 3/2 times cos of 3/4 theta. Only 3/4 of a cycle in the first 360 degrees. How about negative sine of negative 2/3 theta? Half of cosine of negative 4 theta. And finally, negative 2 times cosine of 3/2 theta. Okay, thanks very much.